Swayam Prabha. Digital India. Educated India.
Well, good morning. In the last class you will recall we talked about the shock Hugonot and then we talked about the Rankine-Hugonot equations and also about the Rayleigh line. What did they represent? Let us quickly review it. We were interested when a blast wave gets generated, maybe in the streak diagram, you have T versus Rs. The blast wave gets started at a high velocity and keeps decreasing until it becomes an acoustic wave. It keeps decreasing in strength. We are interested in finding out as the blast wave progresses, maybe when it is at this radius, the wave is here, it gets started over here. When it is at this radius, well, it is over here. We would like to know what is the pressure behind it when the ambient pressure is P0. We would like to know what is the pressure, that is the jump in pressure, and also the wind effect, what are the velocities behind it which give the impulse. Therefore, to be able to calculate the pressure at the different points as the blast wave progresses, we wanted to know what is the value of pressure, we wanted to know what is the value of the velocity, we wanted to know what is the temperature, etc., as the wave progresses. To be able to do that, we found that the problem is a little complicated because the wave is decaying. Well, a particle which enters here gets progress like this, it is also affected by the subsequent motion of the wave. Maybe at this particular time the wave is here, the particle is here, and therefore, the problem is terribly transient, it is unsteady, and therefore, it becomes difficult to do this actual problem, which we will anyway do, but to get a feel for the problem, we wanted to first do the problem of a constant velocity, let us say drs by dt is some fixed value, the shock is moving at a value, let us say rs dot. When the shock is moving at rs dot into a medium whose pressure is P0, whose density is rho 0, let us say whose temperature is T0, and we say this is a quiescent medium, that means it has no velocity. I want to find out what is the pressure, density and temperature behind the wave and also the velocity behind the wave. We wrote the equations for this particular one, namely the mass conservation, the momentum conservation and also the energy conservation relations, and solve these equations in the frame of reference of the shock stationary. Let us put it together here. I have the shock here. Instead of the shock moving at a velocity rs dot, I made the medium move towards it. The medium at rho 0, P0 and T0 now moves towards the shock at a value rs dot because the shock is now stationary, and I was interested in finding out, well, the velocity behind the shock is now u over here. I have rho, p and temperature, which are the parameters behind the shock wave. Therefore, now I have rs dot over here, therefore, the velocity is equal to rs dot minus u over here, and this rs dot minus u I called as u1, and therefore, we solve the problem of maybe u1, maybe p, rho, t behind it. I have the value rs dot of the medium moving towards it, it is moving over here. I have P0, rho 0 and T0. And what did the shock Hugonot do? It related the pressure behind with the initial value of the pressure. It also related the density to the initial value of density, and we got a curve, namely we had pressure versus 1 over rho. For the initial condition, let us say initial condition is P0, the initial condition is 1 over rho 0, this is my initial point. I have a family of points for different velocities of rs dot, and this is what we called as the shock Hugonot. We went one step further, we were not interested in this alone, we wanted P by P 0 divided by 1 divided by rho 0, for which we said yes, I could modify my Schoch-Hugonot equation to give me what we called as Rankine-Hugonot equation, and we got P by P 0 as a function of 1 divided by rho 0, in which case my initial point becomes, let us say, O 1.1, I have the Rankine-Hugonot equation which predicted this particular curve. Now, this curve was for a series of RS dots, because the shock velocity did not come in this picture, and therefore, to be able to predict the shock velocity, what did I do? I had to draw the Rayleigh line, which was the momentum equation. Mind you, what was the momentum equation? Momentum equation of rho naught RS dot square is equal to P minus P 0 divided by 1 by rho 0 minus 1 over rho. This gives me explicitly the value of RS dot, and therefore, for a given value of RS, I have a Rayleigh line, and this gives me the pressure and the density behind the particular wave. Well, this was done pictorially using the Rankine-Hugonot equations and the Rayleigh line, or the Schoch-Hugonot and the Rayleigh line, which gave me the velocity of RS dot over here. Let us put it down, it is Rayleigh line over here. But I found that even though graphically I can do, can't I do the problem and get an analytical expression for P by P 0 as a function of RS dot and as a function of the initial conditions, let us say P 0 rho 0, and this is what we wanted to do. To be able to do that, we said, well, P by P 0 is a non-dimensional number, rho by rho 0 is a non-dimensional number, why not express RS dot also as a non-dimensional number, and we expressed, therefore, we talked in terms of shock Mach number is equal to RS dot divided by the initial sound speed. That means, you have the conditions over here corresponding to sound speed in the upstream side, that is in the stream in which the shock is propagating. Behind the shock, I have the value of sound speed, which is A over here. Therefore, we did this, and what did we get? We got the momentum equation in the particular form. We got P minus P 0, or rather the ratio, because we are not considering explicitly the value of pressure. We got P by P 0. Let me put it down. 1 plus gamma into the shock Mach number squared divided by 1 plus gamma into m squared behind the shock. Let's again qualify this equation, because we are going to use this to be able to predict the P by P 0 in terms of ms square. Therefore, now we have the problem, the shock stationary, you have the gases upstream at condition P 0, rho 0, T 0, and the value of A 0. Well, A 0 is the shock, is the sound speed ahead of the medium in the undisturbed medium, which we derived in the first class as equal to gamma P 0 by rho 0, and this moves towards the shock Mach number is ms over here. With the shock stationary, this medium moves at a velocity ms over here. Behind it, it moves away from the shock at condition m over here. The pressure is P, the condition is rho, the condition is T over here. Therefore, we found P by P 0 is given by 1 plus gamma ms square, that is the Mach number of the gases which is moving in the frame of reference of the shock towards the shock at a Mach number ms, and leaving the shock at a value of m. Well, gamma we considered to be the specific heat ratio, and being a perfect gas, we assumed that gamma here and gamma here are the same. Well, today we want to solve this equation explicitly in terms of P by P 0, and having noted that already we have P by P 0 in terms of m and ms, if I can get a relation between m as a function of ms, if I can solve for this, well, I can substitute the value of m in terms of ms over here. That means, I have ms over here, instead of m over here, I replace it by ms, I get P by P 0 in terms of ms, and that is what we want to do. Therefore, to do that, let us go back to this particular equation and simplify it in terms of, let us say, I want to get rid of m square, or rather I want an equation in terms of m and ms. Therefore, we again note, well, the sound speed upstream over here is given by A square, I again write the expression which I just wrote, is equal to gamma P 0 by rho 0. I also know that the sound speed behind the shock wave is given by the property gamma P by rho, and therefore, if I take the ratio of these two numbers, I get A 0 square divided by A square is equal to, now I get P 0 by rho 0 into, I get, this comes in the denominator, I get rho by P, or rather this gives me P 0 by P into rho by rho 0, which now I can simplify. I can write the expression for P by P 0 from this expression. Let me write it here, P by P 0 as equal to P by P 0. I bring it here, I write it as equal to P by P 0 is equal to rho by rho 0 into A square by A naught square. All what we have done is I take P by P 0, A by A naught square into A square by A 0 square into rho by rho 0. Now, I already know the value of P by P 0. If I can somehow get the value of rho by rho 0, therefore, let me put it in terms explicitly in terms of rho by rho 0, which I do over here. I get the value of rho by rho 0 as equal to P by P 0, which is equal to 1 plus gamma ms square divided by 1 plus gamma into m square, well, into I get this is equal to A 0 square by A square. All what we have done is rho by rho 0, I get A 0 square here and I substitute the value of P by P 0 over here. Now, see, we already know the value of rho by rho 0 from the continuity equation. Let us go back to the basic mass conservation equation of the shock. Let us go back over here. What is it we find? Well, you have the shock coming towards you have the free stream gases coming towards the stationary shock in the frame of reference of the shock with a mass flux rho 0 into r s dot, leaving with a density rho with a velocity u 1, and therefore, you will note that this is the mass conservation we had, namely rho 0 into r s dot is equal to rho into u 1. Now, let us simplify it little bit, let us put it in terms of Mach numbers over here such that I can replace, therefore, I say rho by rho naught is equal to r s dot divided by u 1. Now, I want to express it in terms of Mach number, r s dot is equal to ms into A 0, sound speed into the Mach number of the free stream gases which is moving towards the shock is equal to r s dot. This is equal to u 1, which is equal to m into A 0. Therefore, substituting this value over here, what is it I get? I get now ms into A 0 divided by m into, mind you, this should not have been A 0, it should have been A, because the sound speed behind the gases is A, m into A over here is equal to A 0 square divided by A square from this equation into 1 plus gamma into ms square divided by 1 plus gamma m square over here. Well, in this equation, if I now simplify, I get A 0 square becomes A becomes A, and therefore, the final equation now I get ms by m is equal to A 0 by A into 1 plus gamma ms square divided by 1 plus gamma into m square. This is the equation I get. In other words, I have been able to relate m with ms. The only thing which is still pending is I have the value of A 0 by A. Can I again get A 0 by A in terms of either ms or m or both? That is the question which we have to ask ourselves. Therefore, to be able to do that, we realize that the sound speed, when we talk of the sound speed, we know it is something like the internal energy of the gases. Therefore, we say, well, A 0 must be related to T 0, A must be related to the temperature behind the shock wave T, and therefore, can I somehow use the energy equation for the across the shock to be able to do that, and therefore, we say, well, I have the shock which is travelling, I have the enthalpy here which was H 0, I have the enthalpy here is h over here, I have the velocity rs dot with which the gases are moving in the frame of reference of the shock wave being stationary, I have u1 over here. We talked in terms of the control volume, and what did we say, that the equation across the control volume becomes h 0 plus rs dot divided by 2 kinetic energy plus enthalpy is equal to h plus u1 square divided by 2, or rather from this particular equation I get, if we were to put the terms here, we say h minus h 0 is equal to half into I get rs dot square minus the value of u1 square, h minus h 0 is equal to half into rs dot minus u1 square. And what is h minus h 0? Let us remember that we are doing this problem only for a perfect gas, because we said for a perfect gas dH by dt is equal to Cp, and therefore, this becomes Cp into T minus T 0 is the change in enthalpy, which is equal to the change in kinetic energy. And what is Cp? You will remember we said Cp minus Cv is the specific gas constant R. Therefore, Cp we got it as equal to gamma R divided by gamma minus 1. Please recall this, gamma R divided by gamma minus 1 into T minus T 0, and therefore, this particular equation which balanced the enthalpy and kinetic energy ahead with the enthalpy and kinetic energy after the shock gave the equation in the form, let us just put it down before I solve it, into equal to gamma R divided by gamma minus 1 into T minus T 0 is equal to the value of half into rs dot square minus u1 square. Now, what is the aim? I would like to get the expression for A by A 0, because I get temperature over here, I get temperature over here, this temperature is reflection of the initial velocity of the gases, this temperature is the reflection of A, that is the sound speed behind the gases at the temperature T over here. I know well gamma RT, gamma P 0 by rho 0 is equal to gamma RT 0, rather we have gamma P 0 by rho 0, P 0 by rho 0 is equal to gamma R T 0, and this is equal to the value of the sound speed in the free stream medium. I have gamma P by rho is equal to A squared gamma R T, which is equal to A squared behind it, and therefore, this particular expression now can be rewritten in the following form. Let me rub it out. We are not doing shock Hugonio now, we are trying to get an explicit relation between P by P 0, and therefore, maybe using these two relations I get over here gamma R T is equal to A square minus A 0 square is equal to, I get over here into gamma minus 1 divided by 2 gamma R T minus gamma R T 0 is equal to A 0 square minus A 0 square, gamma minus 1 comes over here, gamma minus 1 by 2 into rs dot square minus u1 square over here. Now, if I were to bring A 0 and rs dot together, I take it on the other side, I get A 0 square plus gamma minus 1 divided by 2 into rs dot square is equal to, now I am left with A 0 over here plus I have gamma minus 1 divided by 2 into A 1 square over here. Now, if I were to take A 0 outside over here, I get A 0 into 1 plus gamma minus 1 by 2 into rs dot by A 0 whole square. Rs dot by A 0 is equal to ms, which is the shock speed, or the equivalently in the frame of reference of shock stationary, the Mach number at which the gases are approaching the shock wave. Similarly, I take A square over here, I get 1 plus gamma minus 1 divided by 2 into u1 by A square, which is equal to the Mach number behind the shock, and therefore, this was A square mind you, and therefore, I get A 0 square divided by A square is equal to 1 plus gamma minus 1 divided by 2 into m square divided by 1 plus gamma minus 1 by 2 into ms square. Now, I am able to get the expression for a 0 by a, which in terms of ms and m. Therefore, I put that expression over here, and what is it I get? Let us put the final expression on the board. I get the value ms by m is equal to a 0 by a is equal to under root of 1 plus gamma minus 1 by 2 into m square divided by 1 plus gamma minus 1 by 2 into ms square. Now, this was not ms by m, this was equal to the value of a 0 by a. Therefore, ms by m I substitute this is equal to a 0 by a into the value of 1 plus gamma ms square divided by 1 plus gamma into m square over here. Now, what is it you find in this expression? You have ms and m, msm, msm, rather I am able to get the dependence of m as a function of ms, which is what we wanted to do. But then this equation is a little clumsy with all this, therefore, I take square on both the sides, I get ms square divided by m square is equal to the square root vanishes 1 plus gamma minus 1 by 2 into m square divided by 1 plus gamma minus 1 by 2 into ms square into I get this was square over here. Similarly, this expression becomes square 1 plus gamma ms square divided by 1 plus gamma m square whole square. In other words, I square this term, I get 1 plus gamma minus 2 m square divided by 1 plus gamma minus 1 by 2 ms square, I square this, and this is my final expression which I get. Now, this equation must be useful for me to be able to predict the value of m as a function of ms. Mind you, ms is known because the shock velocity for a particular shock velocity I want to get the value of the Mach number behind it. Therefore, I can find out m. But how do I solve this equation? We first note the following. We note, well, this particular equation has m square term. Well, it will have m square term, therefore, m4 term. It is quadratic in m square. Rather, if I were to say m square is equal to x, this equation reduces to the form something like ax square plus bx plus c equal to 0, where x is equal to m square and we know anyway ms square, and therefore, I can solve this equation for x, and similarly I now know therefore, the value of m specifically as a function of ms. Little bit of algebra is involved. I will not solve this equation, but I will give you the result, and it is quite simple. You just put m square is equal to x, therefore, m4 becomes x square, m square becomes x, it gives this form, and you say, well, I have to solve this, x is equal to minus middle number plus minus under root of middle number squared minus 4 into the first into the last number divided by 2 into the first number is the value of x, and when I solve for the value of ms, I get the result as the following. Let's get this value. Let me put this value down. The value I get is, let me write the expression. I get the value of m square as equal to ms square plus 2 over gamma minus 1 divided by 2 gamma divided by gamma minus 1 into ms square minus 1. Therefore, we have succeeded in getting from looking at the non-dimensional form of ms square mm square a relation between the Mach number behind the shock and the Mach number ahead of the shock in the frame of reference of the shock itself. This particular value of m square can again be simplified. After all, you have this, you bring gamma minus 1 by 2 here, and what the expression works out to be 1 minus gamma plus 1 divided by 2 gamma into ms square minus 1 divided by ms square minus 1 plus the value of gamma minus 1 divided by 2. This is the value of m square which I get by. This form is to be expected. I have ms square minus 1 gamma minus 1 divided by 2. I am simplifying it. This is the final form what I get. Therefore, we are able to get the Mach number behind the shock as a function of Mach stream upstream of the shock for the particular case of the shock stationary. Let us discuss this equation before I explicitly get the value of pressure, that is P by P 0, rho by rho 0 and other parameters which I wanted to do in this particular analysis. Therefore, coming back to the discussion of this equation, what does this equation tell us? Let us quickly try to see what are the limits and what is that equation going to give us. Well, if the wave is something like an acoustic wave, or if the Mach number is 1, like ms is equal to 1. If ms is equal to 1, I find, well, ms is equal to 1, the numerator here is 0, the value of this becomes ms square is 1, 1 minus 1 is 0, therefore, m square is equal to 1, and if m square is equal to 1, I get m is also equal to 1. On the other hand, if I get ms, I take the other limit, extremely strong shock wave travelling at infinite speed. If ms is equal to infinity, what is going to happen? Well, I cannot get infinity here, therefore, I slightly modify this equation. I want to put in terms of 1 over ms square, because then I can put a 0 over here. And what is it I do? Well, let us put it down, 1 plus, I get gamma plus 1 divided by 2 gamma. Let us divide the numerator and denominator by ms square. I get 1 minus 1 over ms square divided by, I get 1 minus 1 over ms square, because I am dividing, plus gamma minus 1 by 2 into 1 over ms square. And now, in this equation, if I put ms is equal to infinity, well, this becomes 0, this becomes 0 again, and this becomes 0, and what is it I get? I get the value of m square is equal to 1 plus, I get, let us put it down, 1, mind you, this is minus over here, the value of m square is equal to 1 minus gamma plus 1 divided by 2 gamma, because this becomes 0, this becomes 0, this becomes 0, 1 by 1, 1 minus gamma, and this becomes 2 gamma minus 1, that is equal to, I have 2 gamma minus gamma, that is gamma minus 1 divided by 2 gamma. This is the value of m square. Therefore, in the limit of a very strong shock wave, extremely strong, I get m is equal to gamma minus 1 divided by 2 gamma. Therefore, what are the limits? Let us try to put it down in terms of a figure. Well, I have m, which is the dependent which I am interested in. I am looking at the value which is given to me for a particular value of ms, I want to calculate this value. If ms is 1, well, m is also 1. As the value of ms increases, well, m decreases in the limit of very strong shock wave, that is when ms is equal to infinity. What is the value? Well, we take gamma for air is equal to 1.4, let us say, we are doing for atmospheric air, let us say, we get therefore 0.4 divided by 2 into 1.4, and mind you, this is under root, this was m square over here, therefore, this is equal to under root over here, and this works out to be 0.38. In other words, in the limit of very strong shock wave, the value of m is 0.38 and the downstream Mach number keeps decreasing till it reaches a value of 0.38. This is how the shock strength behind to the free stream value of the shock Mach number. This is how it changes, but let us go back to this particular equation and tell ourselves, well, we are considering the upstream Mach number, that is the shock to travel at speeds greater than the sound speed, ms is greater than 1. Whenever ms is equal to 1, I get m is equal to 1. When ms is very strong, I get a smaller value, as the speed, that is the supersonic speed, keeps increasing, well, m keeps decreasing till the value when it is infinite becomes something like 0.38. But if I look at this particular equation and I look at the solution of the equation, even if ms is less than 1, in other words, I am looking at ms being less than 1, then if I solve for ms less than 1, I get m is equal to m to be greater than 1. But if I look at the other parameters in this equation, what happens is the entropy decreases during the particular phenomenon, which is not possible, and therefore, we rule out the conditions for ms less than 1 leading to m greater than 1. I forgot to also tell you that when we solve this quadratic equation, we get two roots. We get one root which is complex, which we ignore, and the root what we got here is the real root which we consider. Well, this is about it. Therefore, we have been successful in getting the value of the downstream Mach number as a function of ms, and now I can use this to be able to predict my value of pressure ratio. How do I do it? Again, I tell myself, well, I have the expression for m by ms, I now know m square over here, I can substitute the value and get the value explicitly in terms of ms. Let me take you to through the slides, because the algebra or the terms are involved. Therefore, let me come back to the slides and do this. What is it I say? Well, I got m square is equal to ms square plus 2 over gamma minus 1 into this particular expression, which I also said could be written as 1 minus gamma plus 1 divided by 2 gamma into ms square minus 1 divided by ms square minus 1 plus gamma minus 1 divided by 2 gamma over here. We also have the expression for p by p0, which is on the board. We write it as 1 plus gamma ms square divided by 1 plus gamma m square. I write the expression for m square as a function of whatever we have over here, namely m square is given in terms of ms square by this expression. Therefore, I have 1 plus gamma ms square in the numerator being the same, 1 plus gamma. For m square, I substitute this particular value, I get ms square plus 2 divided by gamma plus 1 divided by 2 gamma ms square into gamma minus 1 divided by 2 over here. And therefore, now what is it? I have also taken similarly the value of gamma over here 2 over gamma minus 1, and therefore, I get 2 gamma ms square divided by gamma minus 1 ms square minus 1 over here. And therefore, now if I simplify this particular equation, which is straightforward, I get p by p0 is equal to 1 plus gamma ms square divided by, in the denominator, gamma plus 1 into 1 plus gamma ms square divided by 2 gamma ms square minus gamma minus 1, which if I simplify further, I get p by p0 is equal to 2 gamma by gamma plus 1 ms square minus gamma minus 1 divided by gamma plus 1. See, we are able to get the value of p by p0. Let us discuss this particular result. Therefore, what is it I have got? Let's put it down. I already know how the Mach number is behaving. Let's take the role of pressure over here. I get the value of p by p0 is equal to, what is it I say? 2 gamma divided by gamma plus 1 into, I get the value of ms square minus, I have gamma minus 1 divided by gamma plus 1. This is the value of the pressure ratio I get. Therefore, I tell myself, whenever I have a shock which is moving at a value of ms into the free stream medium of p0, rho 0, t0 over here, the value of p behind the shock, p by p0 ratio, is given by this. And what does it tell me? As the Mach number of the shock increases, the pressure increases. In other words, if I were to now write p by p0 as a function of ms over here, for the value of 1, well, I get 2 gamma divided by gamma plus 1 divided by gamma minus 1 divided gamma minus 1 divided by gamma plus 1. Let us see what result we get. Therefore, I get 2 gamma divided by gamma plus 1 minus gamma minus 1 divided by gamma plus 1, and what does it tell me? 2 gamma minus gamma, the denominator is still gamma plus 1, 2 gamma minus gamma, therefore, I get gamma and plus 1 over here, which is equal to 1. Therefore, when the sound speed is 1 here, Well, the pressure ratio is just 1. As the Mach number increases, well, it keeps on increasing. When I have a very strong, that is ms tending to infinity, well, the pressure ratio is very large. In fact, if I am interested in a particular pressure ratio, let us say a value of ms is equal to, let us say 4 or 5, well, I take the value of 5 as an example, ms is equal to 5, that means the shock Mach number is 5, well, this becomes 25, 5 5s are 25, let us put the value down, 25 into 2 into 1.4 for air 2.8 divided by 2.4 minus I get 0.4 divided by gamma minus 1, that is 1.4 minus 1.4, I get 2.4. If I look at this, it is something like 10 times into 28, something like 29 or 30 is the value. That means at a value of 5, I get a pressure ratio of 30. In other words, we find that when the Mach number increases, the crushing pressure or the pressure rise across the shock wave, what happens? Let us again plot it. I have the initial pressure, let us say 1 atmosphere. If the shock is travelling at a Mach number 5, the pressure behind it is of the order of 30. That means it has so much of crushing power that if somebody is hit by the shock wave, he gets compressed. If the shock wave is of Mach 5, he gets compressed by a factor of 30 times the atmospheric pressure, and as the shock wave increases, well, this pressure keeps increasing. Therefore, we are able to write P by P0, and now let us find the last value which we want rho by rho 0. And how do we get rho by rho 0? You will tell me, well, we have already done the Rankine-Hugoniot equations, and what did we get from the Rankine-Hugoniot equation? We got rho by rho 0 in terms of P by P0, and what was the expression? Please go back, let us check it. Rho by rho 0 was equal to gamma plus 1 into gamma minus 1 into P by P0 plus 1 divided by gamma plus 1 divided by gamma minus 1 plus P by P0. This was the expression which we got. Now, I already have the expression for P by P0 over here, namely P by P0 is given by this. I substitute it over here, therefore, I get rho by rho 0 in terms of, that means rho by rho 0 as a function of ms square. Let us do that, I do that in the next slide. Let us go to the next one. That means I have from the Rankine-Hugoniot equation, which I just wrote on the board, rho by rho 0 is equal to gamma plus 1 divided by gamma minus 1 into P by P0 plus 1 divided by gamma plus 1 divided by gamma minus 1 plus P by P0. This is the value of P by P0, which is again on the board, and therefore, I substitute this over here, and therefore, what is it I get? I get rho by rho 0 is equal to gamma plus 1 divided by gamma minus 1 into this particular expression over here plus 1 divided by gamma plus 1 gamma minus 1 plus the value of this expression over here, and which I simplify. I get gamma plus 1 into ms square divided by gamma plus 1 into ms square plus 2. I divide this equation by ms square, both the numerator and denominator, and I get rho by rho 0 is equal to gamma plus 1 divided by gamma minus 1 plus 2 over ms square. Therefore, let me put down this final result on the board. What is it I get? I get the value as gamma plus 1 divided by gamma minus 1 plus 2 divided by ms square, which is the value of rho by rho 0. All right. Therefore, what does this equation tell us? Let us again discuss this particular equation. This equation tells us exactly what the pressure ratio equation told us, namely when ms is 1, that is the sound speed is 1, I get 2 over here, 2 minus 1 is 1, gamma plus 1 divided by gamma plus 1. Therefore, rho by rho 0 is equal to 1 when ms is equal to 1. When ms is very large, let us say infinite, what happens? The value of rho by rho 0 is equal to ms square becomes infinite, this becomes 0, 2 over infinity, therefore, it becomes gamma plus 1 divided by gamma minus 1, which for air, for which gamma is 1.4, I get 1.4 plus 1, 2.4 divided by 0.4, which is equal to 6. Therefore, how does the density ratio change with the Mach number of the shock? We find, well, the ratio of rho by rho 0 as a function of ms when ms is equal to 1, the value of rho 0 is 1. When ms becomes infinity, it is around 6 over here and the Mach number increases. In fact, it does not have to go to infinity to get 6, even at a Mach number of around let us say 4 or 5. Let us work out the value for 5, let us work it out. We get rho by rho 0 is equal to 2.4 divided by 0.4 gamma minus 1 plus 2 over Mach number is 5, 2 over 25, and therefore, 2 over 5 is a 25, therefore, 2 over 25 we are talking of something like 0.08, 0.4 that is 0.48, that means we are talking of a number or something like around 5 or so, even when the Mach number is around 5. That means the value increases from 0 to 6 as you increase, that means as Mach number increases, the density ratio also increases. Therefore, we are now able to say something more. That means, we started from the Hugoniot equation or the shock Hugoniot. We talked in terms of Rankine-Hugoniot equation, which related the pressure and density behind the shock with the pressure and density ahead of the shock. We also talked in terms of Rayleigh line, which helped us to fix the point, namely you had P by P 0 divided by 1 over rho by rho 0. We had the Hugoniot, which was the initial point was 1 1. You had the Rayleigh line. We now are in a position to find the value of P by P 0 explicitly and also get the value of rho by rho 0 explicitly. This is what we set out to do. But how about the velocities behind the shock? That is something on which I spend a minute or two, and that is quite simple. Let us put that thing down. From continuity equation, and what was the continuity? When I say continuity equation for a shock, we are considering the shock travelling at a speed r s dot or else the medium. Now, travelling with a speed r s dot, the density is rho 0, the velocity behind is equal to u 1, the density is rho, the continuity equation is rho into u 1 is equal to rho 0 into r s dot. That means, the mass flux ahead of the shock is equal to mass flux leaving the shock, which is the mass balance, and therefore, from this I get u 1 by r s dot. That means, the velocity behind the shock wave in the frame of reference of the shock wave is equal to, I get now rho 0 by rho, r s dot in the rho 0 by rho, but rho by rho 0 I already have the expression, namely gamma plus 1 divided by gamma minus 1 plus 2 over ms square is the value of this, and therefore, u 1 by r s dot is equal to gamma minus 1 plus 2 over ms square divided by gamma plus 1, and this gives me the velocity of the gases behind the shock front. But we must remember one thing whenever we are solving this, u 1 is the velocity of the gases in the frame of the reference of the shock being kept stationary. That means, I sit on the shock, and when the shock is not moving, but the gases are moving forward, I see the velocity of the gases to be u 1 going away from the shock. But if I consider the actual movement of the shock, and mind you, we had this problem of shock moving at a velocity r s dot, when the medium ahead is quiescent or which is not moving, the value of the gases behind is now going to be, when the shock is moving at r s dot, is going to be r s dot minus u, and therefore, this is what r s dot minus u 1, and therefore, we must remember that this value of u 1 is in the frame of reference of the shock stationary, or if the shock is moving, well, this value is going to be 1 minus u by r s dot, or rather on the right hand side I should get 1 minus gamma minus 1 plus 2 over ms square divided by gamma minus 1, that is gamma plus 1 over here, or rather I should get the value of r s dot minus u as a function of, let me put it on the other side. divided by gamma plus 1. This is the velocity of the particles which are moving along with the shock when the shock is moving. If the shock is stationary, well, it is u1 by rs dot. We have succeeded in therefore telling what are the conditions behind the shock. If I now want temperature and temperature or any other property, let us say temperature, what is it I do? Well, I know I am talking in terms of a perfect gas, therefore, P by rho is equal to RT or PV is equal to MRT, M by V is rho, and therefore, now I get T divided by T0 is equal to P divided by P0 into something like rho 0 divided by rho from this expression, which I can simplify, which I do in the next slide. Let's take a look at it. I get T by T0 is equal to P by P0 into rho by rho 0. We have derived this expression, we know the value of P by P0, therefore, you have 2 gamma, gamma plus 1 ms square minus gamma minus 1 by gamma plus 1, which is for the pressure ratio. I also get the value of rho by rho 0 given by gamma plus 1 divided by gamma minus 1 plus 2 over ms square, and this gives me the value of the temperature ratio. Therefore, I know all the properties behind my shock wave as a function of properties ahead of the shock wave, and we have already calculated the value of u1, and therefore, I have been able to solve the problem. But what is the problem I have been able to solve? Let's be very clear about it. You know, the problem we are solving is for a case of a constant velocity shock. When the shock velocity is constant and I consider my frame of reference of the shock stationary, when the shock is travelling towards my when the gases are travelling towards my shock front with a velocity rs dot, if the conditions ahead is P0, T0, rho 0, I am able to find out the value of P, rho and T, and also the value of the velocity u1 in the frame of reference, or when the shock is moving, I said it is rs dot minus u1. So far so good. Therefore, we also find when I look at the value of u1 by rs dot, it is just inverse, and if I were to plot the value of u1 divided by rs dot with ms, I start with a 0.1, well, it will keep coming down inversely as the density went to the value of 6, this will keep on coming down over here. That means, as the shock velocity keeps increasing, the value of the particle velocity in the frame of reference of the shock keeps decreasing, but in the frame of reference of movement, that is the shock moving, well, the velocity of the gases will keep increasing because it is rs dot minus u1. Well, this is all about the shock relationships for the case of a constant velocity shock, but the problem we are interested is something different. See, we have the problem which actually is the following. We have the blast wave which is not a constant velocity wave, and that is where we got started today. We are interested in something like, let us say in the streak diagram T versus Rs, we start forming with a strong shock wave travelling at high velocity and keeps decreasing. Ultimately, it becomes an acoustic wave wherein the Mach number is equal to 1. It starts travelling with a Mach number which is very much greater. Now, it is a variable Mach number, and how do I use the results what I have derived so far into the case wherein I have something like a decaying shock wave which is a blast wave. This is what I will do in the next class. That means, we know now something about the conditions behind a wave which travels at constant speed, but now I want to extrapolate it to the condition of a decaying shock wave, and this is what I will do in the next class. But I want to remind you one last expression which we could also think of. See, we put P by P0, let me write that expression again, unfortunately I rubbed it out. We had the expression, or let us use the board itself or the slide itself. We had the expression for P by P0 as equal to an expression in the following form. P by P0, we got it as equal to 2 gamma by gamma plus 1 into ms square minus gamma minus 1 divided by gamma plus 1. Supposing instead of having P by P0, I am interested in the value of pressure divided by the dynamic pressure, that is rho 0 is the ambient density into Rs dot square, and I am interested, instead of p by p 0, I am interested in p by rho 0 r s dot square. Therefore, I can write this p by rho 0 r s dot square as p by p 0 into p 0 divided by rho 0 into r s dot square, and I know the value of p by p 0, which I already have on the board, and therefore, this the value of p by rho 0 r s dot square, if I use it, becomes 2 over gamma plus 1. I had the value of Mach number over here, I therefore simplify it, I get 2 over gamma plus 1 minus gamma minus 1 divided by gamma into gamma plus 1 into 1 over m s square. Maybe I will just do this on the board, because this is some expression which I will be using. Let us therefore just complete this part and be done with it. We have p by p 0 is equal to 1 plus, what was the expression we had? P by p 0 is equal to, as Mach number increases, the p by p 0 increases, 2 gamma divided by gamma plus 1 into m s square minus, you had gamma minus 1 divided by gamma plus 1, you will recall this, and therefore, I am interested in the expression of p 0 by the dynamic pressure associated with the shock front moving with a velocity r s dot. Therefore, I write it as p by p 0 into the value of p 0 by rho 0 into r s dot square, and now I substitute this value over here. I get 2 gamma divided by gamma plus 1 into m s square minus gamma minus 1 divided by gamma plus 1 into, this is the value of p by p 0 into p 0 by rho 0. If I were to multiply both the numerator and denominator by, let us say, gamma over here, I get gamma p 0 by rho 0 is equal to a 0 square, and r s dot by a 0 square is equal to Mach number square, and therefore, what I get is I have gamma into m s square, that is 1 over gamma into m s square. Please be careful, gamma p 0 by rho 0 is equal to a 0 square, r s dot square divided by a 0 square is m s square. Therefore, I get m s square over here, I get gamma over here, and therefore, the expression becomes 2 over gamma plus 1 into gamma cancels, m s square cancels, minus gamma minus 1 divided by gamma plus 1 into 1 over gamma m s square. This is the expression we get, and therefore, we find that the value of the pressure, that is p divided by the dynamic head, keeps decreasing as Mach number increases, and this is what we will do when m s is equal to 1. Well, I get a value of 2 gamma minus 1 divided by gamma minus 1 divided by gamma plus 1, which is the value under Mach number 1, which is equal to the dynamic pressure for an acoustic wave, and when m s is very large, equal to infinity, it is equal to 2 over gamma plus 1. Well, these are the expressions for the constant velocity shock relations. Therefore, in the next class, as I said earlier, we will try to take a look at what are the properties, what are the pressure rise across a blast wave, what are the velocities behind a blast wave, and that we will do in pieces, because we told that, well, the problem is complicated because it is totally unsteady, and we will try to take some limits, some conditions for which we will try to do the problem. The conditions we will take are, let us consider the initial phase when the Mach number is very large, Mach number tends to a large number, and for this let us try to do the problem, and in the limit of Mach number going to 1 at in the very far field, let us do the problem and we will get some feel for the problem. Well then, thank you. We meet in the next class wherein we do the unsteady problem.